Okay, I've decided we're going to move back to vectors, but as a continuation of where we left off when we studied force, impulse, and then work, and we saw the multiplication of vectors coming into effect. So I said, let's go back to vectors, and let's take a look at what's going on. And I want to start here with really the fundamentals of the vector and its representation in coordinate geometry. So I do have that favorite graph of mine, right? And then we'll play around with the cosine of the angle and things like that. But first, let's take a look at representing vectors. So if you remember this graph, and I wrote here, or I drew, if you remember in one of the videos, wrote a vector and told you that this is basically AI plus BJ, where the vector is a sum of A units of I, if somewhere here was A, and if somewhere here was B units of J, I and J being the unit vectors in the XY plane, right? So I've stated this is the XY plane, or the IJ plane, if you will, right? Two-dimensional, right? We're not doing 3 dimensions here. So what's this AI plus BJ? I want to just clarify. It's effectively saying I have a vector this way. So this would be, let's say, a vector with 0 j component, and another vector with 0 I component, let's say here, and their sum, or their net effective, if you will, vector is this one here, AI plus BJ. And that's really what it is. But at this point, I also want to highlight to you 2 things. So this here, this point here, coordinate A comma B, as you would say, x comma y, would be the head of the vector. And at this point here, coordinate 0, 0 is the tail of the vector. And that representation of the vector could be written as x of head minus x of the tail times I plus y of the head minus y of the tail, the y coordinate of the tail, so the x coordinate of the head, x coordinate of the tail, y coordinate of the head, y coordinate of the tail, times j. And in this example vector, x coordinate of the head is A, x coordinate of the tail is 0, times I, plus y coordinate of the head is B, y coordinate of the tail is 0, times j. So that gives me the AI plus BJ. If you're still unclear about why the plus BJ, we'll get to that, because we're also going to look at vector addition, right? So I want you to make sure you understand how that vector got written, okay? We'll keep that there. The moment we'll take out everything else, so you know fundamentally what we're trying to do is representing a vector using coordinate geometry, okay? So I'll take all these out. And what I'm going to do now is I'm going to go back to my example of the boxes moving, and we talked about a displacement vector and a force vector, right? Now let's just say you understand the ways of the force, and you're applying a force here of 5 Newton, let's just say you're applying a force of 5 Newton, right, to move this box, to displace this box. Let's worry about the effects. We're only doing vector, so we'll focus on the vector. So I'm not going to draw a string or anything like that. Let's just say you understand how to put this force in effect, and that's what happens. And as you do that, let's say you have a friend who comes and says, hey, I'm gonna give you 5 Newtons as well. So your friend comes in and some mysterious ways, since he's also a master of the force, exerts another force here. But since you both know vectors very well, you've defined your force of 5 Newtons, vector F. This is your vector F, which is the green color. And I'm going to call this, since it's yours, it's F1 vector. You've defined it as being you are no ordinary student of mathematics. You're very precise. And your friend, who also knows mathematics, says, wait a minute, my vector is going to be defined as (3j). All right, what happens now? This is where the effect of the two vectors come into play. So if I go down in between and say, okay, let's take a look at 3i plus 4j, and that's 3, and 2, 3, 4, that's 4. So if I come in somehow as the independent observer and I do this, and I draw, oh, that's your vector, and I define this as vector F1. F1, that's the vector. Written 3i plus 4j. Now I want to say, okay, that's one vector. Let's take a look at your friend's vector, and I come up here and I start drawing your friend's vector. And then you say, no, stop. Somehow you say, that doesn't look right. It appears like it's at another point. Well, and somehow you come and tell me, sorry, it's at another point, and I've calculated mysteriously, with some cool technology, I have calculated that vector to be, let's just say, you come and tell me that you've calculated that vector to be starting here, all right, and let's say 3 units of the y-axis and 4 units of the x-axis. You've told me that that is the vector. All right, that has to be the vector. Ooh. Now, how do you define that vector? Well, very simple. We learn the head and tail of the vector. So that vector's head has x coordinate. And what is this? Say this is 2 and this is 3, negative 3. So this is negative 3 and a y coordinate of 2. Negative 4, negative 5, negative 6, negative 7. The tail is negative 7, 2, 3, 4, 5, and 5. So what is that vector then? That vector would be, if you remember, negative 3 minus negative 7 times I plus 2 minus 5 times j. Well, what happens here? Negative 3, negative minus 7. That's a positive 7, so this would be 4i, and this would become negative 3j. Now if I went back here, I could write this of 4, that's somewhere here, and 3 somewhere here. Now I'm going to write the same vector like this, call it f2, and define it as 4i minus 3j, which is the exact same vector. So understand that. It's an important principle, because whilst you study objects and things like that, don't get confused by where you see the application of the force on a diagram. In reality, because vectors, once mapped into a coordinate system on a two-dimensional plane, and by extension this works even in 3 dimensions, we'll get to that at some point, but for now, on a two-dimensional plane, you can actually write these vectors differently. You can shift them as long as their magnitude doesn't change. That's also a 5 Newton magnitude. This is also 5 Newton magnitude. That is 16 plus 9, and the square root of that would give you 5. Okay, I hope that is clear. So that is about representing vectors and what you can do in equivalent terms by bringing them into this two-dimensional coordinate system. Which also means, and here I'm going to introduce this concept, the net effect of these vectors effectively is on one point on the object when we consider it. And typically that point in the object is called its center of mass. I'm just going to make a note of that. It's a concept that the center of mass. It's a concept. It's like that. It's like one imaginary point within the object where all forces that are acting on it somehow seem to have their basis, their starting point. So you might have a large object, and think of this example. If you've got a double-decker bus, you typically notice that they have to be slower when they turn versus a Ferrari, a flat car, or a Formula One racing car. They can execute a turn much faster. Why? Because the taller bus has an elevated center of mass, which may make it easier for them to tip. But all of that later, when we get into other studies of motion, a heavier object, typically wherever the mass is concentrated, the center of mass seems to be moving towards that, right? This is a concept, and that is important because all your vectors then get applied here. So all of the manipulation of the vector can be done with this basis, okay? It's just a concept, keep that in mind. And also understand how vectors can be moved to get the same effect. So I'll take this out. Now that we know that your friend's vector is there, let's do something. What is the net effect of these two vectors? And we're going to do this in two ways, right? Displacement is along the x-axis. So all of the effect we need should be felt along this axis. So let's play with this, right? Our first, and I'll write this with green, our first understanding is we want to get the horizontal component, F1, horizontal H. What is that? Well, we know if this angle is theta 1, we know that the horizontal component is the magnitude of F1 times cosine of theta 1. And if you know your trigonometry, 4, 3, and 5, right angle triangle, cosine of theta 1 is effectively 3 over 5, adjacent by hypotenuse. If the magnitude was 5 and cosine of theta 1 was 3 over 5, the horizontal component of this vector is 3. Obviously this would be newtons because it's a force vector, but since we're studying vectors now, I just want to, and I'm using the force vector as an example, that is the horizontal component that comes up here. Okay, so now what happens? Let's look at your reference vector here. Perhaps writing that equal to 3. And your reference vector is force F2, and we want its horizontal component is nothing but force magnitude of force vector 2 times cosine of, okay, we need this angle now, theta 2, cosine of theta 2. Again, if you know right angle triangles and basic trigonometry, the cosine of theta 2 is its adjacent side by hypotenuse, which in this case would be 4 by 5. And if you know, and if you try to say, oh, theta 2 is negative, well, if you know your cosine, the cosine doesn't change if it becomes negative, so it would still be same positive. This would be 5 times 4 by 5, which would be 4. So what is also happening is you're getting another vector here, 4. Well, now I have these two vectors in the same direction. What would they add to be? They would be, let us say, if I now represent these, I obviously use the scalar quantity here. Why? Because the theta is providing direction. We're coming to a single plane. But if I now say I have two vectors, and I'll come back here, and I'll define a vector f to be, make this f1 to be, sure, is equal to the sum of just two vectors, which is h as a vector, though by saying it's horizontal I already know where I'm going, but I'm going to write these this way. So adding these two vectors would just mean adding their magnitudes. Well, this vector would be represented as 3i plus 0 j, remember it's horizontal, plus 4i plus 0 j. In coordinate terms, adding the magnitudes easy. It's 3 plus 4, we know that. But what's happening in coordinate terms? It is the same as adding their x components and writing 3 plus 4 I plus 0 j. I should have written this, or rather, here's what I do, just so you understand. 4i plus 0 j. What does that get me? That just leaves me with 7i plus 0 j, which is really just the horizontal vector along the extension of the I unit vector to give me an addition, which if you see, 3 units and then another 4 units. So 4, 5, 6, 7, my net resultant vector is something along those lines, comes up here, straight line there. With me so far, I've just resolved the two components into horizontal axes and added them. Okay? With me, stay there. Okay, now let's forget about all of this. Forget about resolving the vectors and all of that. So we've just done one kind of math and added the two vectors. I don't want to go there. I want to say, no, forget about resolving them, etc. I just want you to add the two vectors. Well, what happens then if I just want to add the two vectors, right? Well, remember what I talked about representing two vectors, right? And how those vectors can be equivalently represented by just changing the tail and head coordinates, and you kind of move the vector around. And let's go back to that first part where I said this is 3i plus 4j. What exactly is that? That's 3i and 4j as two vectors, and this is the result. It's sort of written as if you're adding the two vectors. But if you move these vectors, so if you said you had a vector this way, which is just 3i and 0j, and if you had another vector, which is 0i and 4j, well, you would write them here, but effectively, you could displace these vectors so they're equivalent, right? If you move that vector here, I'm going to do a dotted line, and your result was that. And you could do it either way. You could argue the case that, hey, those are the two vectors, and this is the sum of the two. Well, I'd argue that I could just displace this vector here and connect the first tail to the last head, and I've added the vector. And I can do this any number of times. Mathematically, if you know your coordinates, and you can play with the coordinates, I'm not going to go into the detail. You can displace the coordinates as many times, and you can add another vector if you added another vector here, so a third vector, or in another direction, and got something here, you would still be able to connect the two and come up with a total. And you can add them each time it's this, and then you take this vector, add another vector here, and then you'll get a resultant vector between these two. And this keeps working every single time, and that's because I can create equivalent vectors that act at a common point from where I can resolve them into any single axis to get the resultant vector. And that xy can, I can set this to be my x and a perpendicular line to be y. However, it's within the plane, the vectors add very simply. It's the coordinate of the last head of the head of the last vector and the coordinate of the tail of the first vector that you add, and you will end up with the new resultant vector by adding them up. So it's simply the sum of all of the x coordinates of however many vectors you have, right, times I, and the sum of the y coordinates of however many vectors you have will give you that resultant vector. Something to understand and just keep in mind. Okay, let's go back to this example and see what happens. If I wanted to add this vector now, I could, because I know how to displace him, I could displace this vector 3 units off and 4 units here. 3 units here brings me here. 4, 1, 2, 3, 4 would bring me here to this point, and that would be my equivalent F2. Which would then let me write a new vector here as the resultant vector, but this one would be at coordinate 7, 1, which means that resultant vector is 7i plus 1j. That is 7. So at that point, this is 4, 5, 6, and 7. That is 0.7, or that is the point, the unit, 7 times the unit value. That is the resultant vector. And what would be its component along the direction of displacement? We know, whatever this theta is now, that resultant vector F would have a horizontal component FH, which is the magnitude of F times cosine of theta and you can say that this is just 7. Magnitude of F in this case would be, well, the hypotenuse would really just be the square root of the square of 7 plus the square of 1, which is the square root of 50. And then once you find theta, be like 8.15 degrees, which the cosine of which is 0.9899, something very, very close to 1, and then a square root of 50 is really close to the square root of 49, so you'll effectively end up with 7. You can do the math there to convince yourself, but you'll end up with 7 if you work to the precise decimal. So the result, even by doing this, you get the resultant vector. Its horizontal component didn't change. So by both methods, I hope you can appreciate here what we're doing and what exactly it means by manipulating vectors and why this is important. Now, I'm going to pose an interesting problem here. Since both of you understand vectors and force, you're going to do one thing. You're going to tell your friend, oh, you know what? Let me change my force vector. I'm not going to change the 5 newtons, but I'm going to change my force vector. And he asks how. He said, oh, I'm going to change my force vector now to 4i plus 3j. And you believe that's going to be more helpful to both of you. What happens here? This is your new F1. It's in a different color. I'll let you work the math, but I think you get the idea that you can work the math out, but whilst you try and do it using coordinates, I'm going to do a simpler view. I'm just going to show you what's happening here. That's your new F1, and you can see what happens if I take this and map it out here. I'm going to get that with a resultant vector of 8. The same 5 newtons applied in a slightly different direction, and hopefully it becomes intuitive to you that on what's going on, but you can work the math. But the idea here is for vector addition, you can use this parallelogram method, because instead of putting vector 2 against this one, I could have just taken vector 1 and mapped it here, and I would get the same end result because I would still come back here. So I'll let you work that math out, but there we go. Vector addition and what exactly happens and how the same force magnitude but applied in a different direction of the vector can give you a different result. So the magnitude can be the same, but the direction of the vector can provide an end result when it comes to force. But this becomes important if you have an object moving in a particular direction with constant velocity and you apply a force. If you apply another, let's say a force here, this time it's momentum in that direction, but you've applied a force, you could argue that you could kind of use the vector manipulation to see what's going on. But remember, with vectors, you often want to add the same vector. So if you have a force vector, you're adding a force vector to it, right? You've got to add something of the same type, not of a different type, right? So remember that. But now let's come to the second part of this, right? We talked about work. We talked about work being, I'll probably take all this out. Let's worry about these things. Yeah, we'll take all these out. Right? We talked about work being equal to force times displacement. And I mentioned work is also a vector, and I did kind of address vector multiplication. What we're going to do here is in the two-dimensional plane, in the xy plane, right? You would if you multiply this vector, there is really only one way of doing it, right? And it's often called, I think it's, let me use the term, it's called a dot product. Or sometimes referred to as scalar multiplication. Why is this so? And the reason it is so is because in two dimensions, effectively what happens when you multiply the vector is you're taking the magnitude of something and multiplying it, because you've already set direction. There isn't a further direction to go. You could argue that, hey, I've taken this, mapped it to this direction, taken this, mapped to this direction. Yes, that's fine, but effectively it's like taking this unit vector and adding to its magnitude by, so it's really just saying 5 newtons, well 5 times I, when you bring this here, well we know that's cosine, so that's say 3, so it's multiplying that magnitude by 3. So it's really what I'm doing here is I'm taking, in this case, for this f, I'm bringing its magnitude down here, right, as I move it into any particular axis. And if this is theta, what is really going on here is multiplication. So s vector gets, you add in f vector times f, the s vector. So the s vector is increased, and it's really just like multiplying it with a scalar quantity. Even though we had two vectors here, really what we did was we took this vector, we have a unit vector here, we're taking the magnitude, the component of its magnitude here, and then multiplying this unit vector by that. So that's why when you do it in two dimensions, it's always a scalar multiplication, often called a dot product. When you do 3 dimensions, you will see that there is a cross product, which we would denote this way with a cross, but no, in this case, it's a dot product. So when you see vectors, and what exactly is a dot product? It's easy, if you've guessed it, you're taking the magnitude of the first vector times, well, whichever is your first and second vector, right? The magnitude of that vector, and you're multiplying it with that second vector. So in this case, if you had 5 newtons, you know your theta. If I just use this, 3i plus 4j, that's component is 3. I'll take my displacement vector and multiply it by 3. In this, again, displacement vector in this case is in just one direction. So let's say if the displacement vector was 1, it would be 1i, 0j. If I multiply it with 3, it'd be 3i and 0j. But if that displacement vector had, let's say if it started off being 2i plus 2j, then that component that comes in, if that component resolved to the, if I just say 2i plus 2j is my displacement vector here, and if this angle was the new theta, hypothetically, just hypothetically, if that says 30, right, 30 degrees, and I know cosine of 30 degrees is 0.86, I think, then I just multiply both coordinates by the same value, and I would end up with, let's say, 3 point something would multiplied by 0.86, 2 by 2, that would be my product. Which means I've taken a scalar value, which is the magnitude, and I multiplied both of the coordinates of this. So it's like saying, I now will write this, right, which is nothing but a component component of f, so I'm going to call this fc, which is a scalar value, and I'm going to multiply this, right? This is just a component, multiply this by the s vector, whatever is this s vector, right? ai plus bj, which would just mean my new vector would be this component times a I plus this component times b j. That would be my resultant vector. And that is why it's a scalar multiplication. Very different from vector multiplication or cross product, where you're actually going to see how the two coordinates of two vectors come together, but they'll often result in a third vector in a plane perpendicular. So you leave the xy plane and you come into a perpendicular plane. So that's why I said it's better studied when we do 3 dimensions. And we'll probably get to it when we do torque or momentum or something like that, which has 3 dimensions. But in 2 dimensions, it's as simple as this. Your scalar multiplication is what happens when you try and multiply 2 vectors. And that's why what we're studying is just this type of vector multiplication. We'll get to vector cross products sometime later, right? In this simple terms, we don't have a movement outside of this plane. Everything is happening in this plane. So we can conveniently take this one vector, get a scalar component of it, which is bringing it here into this direction. And again, I've just drawn them. This is a horizontal line. They may not be, right? They may both be at an angle to the xy axis, as I've illustrated here. But whatever is the angle, it's the cosine of that brings the magnitude here, and then both coordinates of that vector get multiplied. Hopefully, this gives you an understanding of multiplying vectors using dot product or scalar multiplication method and what that means. I will leave you here with this. Hopefully clarifies a little more, gives you an idea of how the work done would be calculated if you know force and displacement, and you can get that. Obviously, if it comes to impulse, which is force and time is a scalar quantity. It is just multiplying the force vector with the time component. So both the units of the force vector get multiplied with the time component, and there you go, you get an answer. All right. Hopefully this clarifies and gives a little more perspective on vectors and how you would manipulate them. And when we get to the 4th concept, we'll start doing power and energy and some of the other things, and then we'll get to doing some exciting problems and exercises. But so much for vectors. Good luck.